In this section, we're going to explore finding the area of shapes using a process called dissection. To start off, though, we're going to look at different shapes of rectangles and right triangles, because that's going to be our goal, is to eventually break everything into those shapes. So the first one here, we have the area of this rectangle, dimensions of 4 by 8. So the area is just 4 times 8, which is 32 inches squared. For the triangle, we're going to use the formula 1/2 base times height. Our base is 8, and our height is 6. When we take 1/2 of 8 times 6, that's going to give us 24 centimeters squared for the area of that triangle. And in the third diagram, we are going to solve the area of this triangle using that process called encasement that we've previously explored. Again, this potentially we might be using encasement again in this section, so we want to make sure that we're pretty familiar with it. So our idea of encasement is to draw a rectangle around this triangle, find the area of the rectangle, and then subtract. So we know that 1, 2, 3, 4, 5, so that is a width of 5, and the other dimension is 5. Turns out it's a square. We're going to find the area of the square by doing 5 squared, that's just 25. And then we're going to find the area of each of these triangles and subtract them away. So let's see, this is a 4 and a 4. So the area of this triangle is 1/2 of 1 times 5. So 2.5. Same thing over here. Same dimensions. And the area of this triangle will be 1/2 of 4 times 4. 8. So when I add up the triangles, I have 2.5 and 2.5 is 5. Add 8, I get 13. Subtract them away. My area is 12. So in activity 1, we're looking at shapes that are in a, not in a coordinate plane, but just a regular old plane. And we're trying to break them apart. So our first one here, I recognize anyway that there's a rectangle here in the bottom, and it looks like what's called a trapezoid up at the top. So to find the area of these, I don't think I can really need to do anything down here, but I think up top I need to break this shape down so that I have 2 right triangles on either end and a rectangle in the middle. All right, now we know that this whole base is 24 because if this is a rectangle, then that side has to be the same. I know that if this is 12, so I'm going to highlight this part right here. This has to be the same thing. Because again, opposite sides of a rectangle are equal. So if this is 12 and the whole thing is 24, these two pieces would be the same, so they're both 6s. From there, I notice that I have my right triangles on either side with sides 6 and 10 being the hypotenuse, so it looks like that our height there is going to be 8. So to find the area of this shape, all I'm going to do is I'm going to take 24 times 8, and I get 192. Again, that's for my lower part. And then I'll find the area of each of these 3 and then put it all together. So the area of the rectangles is 8 times 12, which is 96 inches squared. And then the area of each of these triangles is going to be 1/2 of 6 times 8, which is 24 inches squared. So that's this one here, and it's also that one. So next I'm going to add these together. So I'm going to take 192. I'm going to do this on my calculator to be sure. So 192 plus 96 plus 24 plus 24 gives me 336 for my area. And perimeter is all the outside shapes, or all the outside sides added up. So I'm going to take 24 plus 8 plus 8, so that's at 40, plus 10 is 50, plus 10 is 60, plus 12 is 72 inches. Here's a good one. This is called a regular hexagon. All sides are equal, and all interior angles measure 120 degrees. So if we want to find the area of this, our idea of dissection still applies, but we're going to try and break this shape up. If I do it like that, it doesn't quite work out nicely. I'm going to keep it going and draw on these other diagonals. And if I've done this right, and I'm pretty close, we should get 6 triangles. that are all equal. Now, we said that this measure here at the base angle is 120, so all of these are going to get broken down into 60s. All the way around. So if we have triangles that have all 60-degree angles, and again, these are all 60 in here as well, then those are equilateral triangles. We've already said that they're congruent, they're all the same, so we just have 6 of them. To find the area, I can find the area of one of the triangles. So again, the triangle it's equilateral, so it's 1/4 6 squared root 3, which would give us 9 root 3. That's the area of one of them. But the hexagon actually has 6 of them. So to find the total area, I'm going to do 6 times 9 root 3, which is 54 root 3. So my area of that hexagon is 54 root 3 meters squared. My perimeter is all the sides added up. Well, there's 6 of them, so 6 times 6 would give me 36 meters. And on a question like this, we have a couple options, and I'm going to show you, I think, to me anyway, what's the easiest option to do. One option is you can break this up into rectangles and right triangles, but I like the idea of pseudo-encasing it. In other words, if I were to extend this line up and extend this line over, what we end up getting is just one big giant rectangle. But the reality is it's not quite a rectangle because we've shaved off this one little corner. So to find this piece right here, I'm going to find this side, which is 15, and take away 11, and that's going to give me a 4. This whole side is 10, but I've used up 7, so I have 3 left over, and I've got a right angle there. So my missing side here then would be 5 if I complete the triple. Well, to find the area, I'm going to find the area of everything all together and then shave off that little corner. So the area of the big rectangle is 10 by 15, which would give me 150. And then I'm going to subtract off the area of this little triangle up at the corner here, which is 1/2 of 3 times 4, which is 6. So 150 minus 6 would give me 144. So that's my area, and units are yards, for that shape. Perimeter, again, add up all the sides, so I've got a 10 and a 15 is 25, plus a 7 is 32, plus 11 is 43, plus 5, I get 48 yards for my perimeter. So that's a little sampling of what we can do in a plane. Let's take a look at ones that are in a coordinate plane. You're going to see that our process really hasn't changed a whole lot. So if we're looking at number 1, again, it looks like that trapezoid shape. So if I want to find the area, I'm not concerned about perimeter this time, just the area. I'm going to break this apart, and it's really nice to do vertical and horizontal lines because they'll break it up into rectangles and triangles a little bit more easily. So if I draw that vertical line here and here, then I have a rectangle here and 2 right triangles. So now it's a matter of just kind of counting the number of squares to get our dimensions. So I see a height of 3, a width of 4. So the area of that rectangle would be 12. Again, this is a height of 3, a base of 2, and this one has a base of 3. So they're not congruent triangles on either side. I have to calculate the area of each one. So to find the area of this one, I do 1/2 of 2 times 3, which would give us 3. And the area of this would be 1/2 of 3 times 3. So the area is 4.5. So to find the total area, I'm going to take 12 plus 3 is 15 plus 4.5. And I get 19.5. I'm not worried about units because there were no units given to me. Technically, I could put units squared, but I don't really know what they are, so I'm not concerned with it. I do want to take a look at one more problem, though, because I think it's an interesting idea and it will involve that property of encasement. Just looks like a trapezoid, but kind of tilted to its side a little bit. So I think the best way to solve this is definitely to encase it. So we're going to drop that line down, make sure I go far enough, and over this way, and up, and over. So we have this big rectangle of dimensions 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, it turns out it's a square again. That's cool. Again, that's the entire side. So now I want to break this apart into the triangles, and I see 4 of them. So this triangle has a base of 8 and a height of 8. This one has a height of 1, base of 5. And see, we've got a 4 and a 4. And again, remember that when you're finding, you're doing encasement, if the entire side is 9, these two dimensions here have to add up to that because together they make the segment. So this is going to have to be a 1. If this whole thing is 9, I've used up 4, then I've got 5 left over. So the area of this triangle is going to be 1/2 of 8 times 8. So that's going to give us 32. The area of this triangle is going to be 1/2 of 4 times 4, which is 8. This one will give us 2.5, as will this. So the area of the square is 9 squared, which is 81. And the area of the triangles together, see, 32 and 8 is 40. 42 and a half, I get 45. So when I subtract those, I'm going to get 36. Again, that's going to be the area. Encasement works, dissection works. I mean, it's just a matter of which one would be easier for you. You could technically do this with dissection, but it's far more complicated. So I want to show you that there's definitely ways to do it with either process, and you get the right answer.